So this is our last topic, topic 3, solving inequalities. Inequalities is a word we've used already in this course. Inequalities are these sorts of symbols here, the less than, the greater than, less than or equal to, greater than or equal to. So these symbols here. And today's topic, it's not, how do I phrase this? It is not necessarily calculus yet, obviously, because we're still in the pre-calculus kind of section here. What I want to do today is build some skills that I know you're going to need moving forward. One of the skills is to be able to factor. Another skill is to be able to know how to use a number line and to be able to use interval notation as a way of expressing a solution to inequalities. You may also need to use this sort of skill when we do something later called curve sketching. So, I mean, this whole section that we've been doing, this pre-calculus bit, is really just building some of the transferable skills that we're going to need going forward in terms of calculus. So again, we're not quite to the point yet where we're really doing something that we call calculus. We'll do that in the next set of lessons on limits. But boy, these are still skills that we need to have. So let's do some examples. Before I start, I should point out that you may have seen this before. This sort of stuff comes from the 20-1 curriculum. You're supposed to be able to use inequalities in 20-1. So, okay, let's give this a try. If I were to ask you to focus on this particular inequality right here, the first couple things I'd point out is just some of the vocabulary and some of the notations. First of all, this is a single variable sort of inequality. Single variable because there really is only one variable, right? There's just x's. It is possible to deal with this when you have x's and y's. There's ways of doing that. But for right now, if there's only x's, what we're really asking you for is the domain. We're looking for the x values that make this true. And I mentioned in our last lesson, it's kind of unfortunate that the word range has already been co-opted to be used to talk about y values on a function, the outputs on a function. But I mean, essentially what we're looking for is we're looking for the range of domains, the sliding scale of x values, which make this true. Let's give you an example here. Let's say x was 0. If x was 0, I'm just... a mistake there. If x was 0, I'm just going to do a quick little bit of mental math. Well, that would make this 0, so that whole thing kind of goes away. That would make this 0, that makes this whole thing go away, which means that you'd be left with -8. And then you'd have to consider how an inequality works. An inequality is basically, there's a range of values that fit, right? Is -8 one of the many values that is less than 0? And you'd say, yeah, it is. So x is 0 is a valid possible solution. Let's just try for sake of argument. Let's say that x was a million. Right? I'm not going to do all the work here, but if you did 3 times a million, that'd be a really large number once you square the million. And let's say you subtracted 5 million. It'd still be pretty large, right? It'd still be greater than 0 for sure, right? And then if you minus 8 more, that'd be pretty irrelevant because you've got a million squared times by 3, right? So hopefully you'd agree that, yeah, it looks like, man, there's some numbers up there that... hang on, no, that wouldn't work now, would it? Because I got ahead of myself. That would not work. If x was a million, this wouldn't be valid because then this really large number here would not be less than 0. So the goal here then is to try to find out like the ranges of values that that work. So here's the skills I want to show you then. First thing we want to do is we want to solve it as though it is an equality. So just pretend this was an equal sign and solve it as though it's 3x squared minus 5x minus 8 equals 0. Just do that. So hopefully you're familiar with different methods of factoring, or at the very least the quadratic formula. I like to remind kids how to factor using this sort of method. You're going to look for numbers that add to give -5 and multiply to give -24, which is 3 by 8. That's how that works. Now, I don't care how you factor. You just need to have your own method that works. But this looks like it should work if you use a positive 3x and a -8. So I'm just going to solve this. And I mean, similar to before, if you have questions and I lose you here, make sure you ask me when you get a chance during our face-to-face time in the videos. But hopefully you are able to do something like this and you know how to factor. It's a grade 10 skill, actually. All right, all of this was really to accomplish this goal. I wanted to find the values where what x would be equal to. Now I got to point out here, though, this really is not true because this is if it was equal. But it's not equal. It was less than. So now we can't necessarily assume that it just means that x is less than 8 over 3 and x is less than -1. That may not hold true. You can't just say, well, maybe it's this and maybe it's this. Because actually that's kind of redundant. If x is less than 8 over 3, then that accounts for 0, but if x is less than -1, most of those numbers have already been accounted for in this particular bit here. So we need to do what I've been taught and what I teach as. It's called finding a test point. And so these test points right here, I'm going to put them on a number line, just as a way to represent this visually. So I know it's not actually equal to these numbers, but let's pretend that it was for a second. And let's plot -1 and 8 over 3. What this does is it really creates 3 sections of domain values. You have the lowest section where it goes from -1 and below. We have the largest section where it's greater than the 8 over 3 section. And then we have kind of our in-between middle section where this would include -1, 0, 1, even 2 gets to that far. 3 would be over here, right? 3 would be just to the right of 8 over 3 because that would be 9 over 3. So we basically have 3 ranges of domain. Again, poor definition choices, right? We have 3 different ranges, though, that we need to consider whether or not it's possible that those x values fit our original equation. Well, inequality, it's not actually an equation, is it? So now we do a test point. So I'm going to pick a random test point, let's say -5. Right? -5 is clearly in this lowest section here, right? It's below -1. So I'm now going to plug in -5 into my original inequality, and we're going to test to see whether or not it actually holds true. So -5 squared would be 25 times by 3. This gives you 75. -5 times -5 will give you positive 25. So that gives you a running counter of 100. And if you minus 8, again, the true value doesn't really matter. I believe it's 92. But we can just kind of estimate this now. Is 92 going to be less than 0? And the answer to that is clearly no. No, the larger these numbers get, they're actually still going to be greater than 0 by the time we're done. I mean, as we go further into the negatives, here's why. This number right here, you're going to square it. So if it's a negative number, it ends up becoming positive anyways. And then right here, this negative number will times by another negative number, making it essentially positive, making it even further positive. And then by the time you're done, you'll subtract 8. But like we saw in this example here, by the time you have positive 100 as your net right here, and you subtract your 8, and it doesn't really matter, right? So what I know then is that this is not where we have answers. There are not solutions in this particular set. So let's try another section. Let's try a number that's clearly between -1 and 8 over 3. And I already did that earlier a few seconds ago. 0 is definitely in that section. And if I were to do a quick little do this in your head. And by the way, you need to practice your numeracy skills in your head. Like, don't use your calculator. If you have any aspirations of going off to university and getting through high university math and calculus, if you are pulling out a calculator to do -2 times -2, and doing basic mental math in your head, you won't make it. So you better start practicing now using, being able to do some stuff in your head. Because, I mean, second of all, you're not even going to be allowed a graphing calculator. You need just a pure scientific calculator, like a $15 cheapo one. So please don't be doing this in your calculator. Do it in your head, just for the mental practice. So anyways, let's say you use 0 as your value, right? Do some mental math. 3 times nothing times nothing. Well, that's just nothing. 5 times nothing is nothing. So you're left with -8. Is -8 going to be less than 0? And the answer to that is yeah, it is. So therefore, it looks like we do have some values that should fit in here. By the way, I should point out what I'm doing here is I'm testing one point in the range of values we're looking for. And the assumption is, and this is a valid assumption, by the way, that all of the points between the -1 and the 8 over 3, all of them within there should actually hold true. So if I test 0, it should hold for 1 and it should hold for 2. I don't actually have to test every single one. I can just test a few here and there to see where the trend is going, right? I can explain that a little bit more later, but maybe think of it this way. If you were to have a graph right here, here's a nice quadratic graph. If I were to ask you, where is the graph less than 0, you might say, well, right here it's less than 0. And so we just proved that 0 for x is less than 0, but 1 should also hold, and 2 should also hold, and 3 should also hold, because all of these points down here should be less than 0. Whereas this section and this section over here, they're clearly greater than 0. And so when we do a test point on this third section here, hopefully it won't hold true. So let's try a number that's greater than 8 over 3, like, say, 3. Right? 3 is 9 over 3. It's just slightly more. We'll try it out. So if we do this, plug in 3, you'll have 3 times 3 squared. That's 27. Minus 5 times 3, that's 15. So let's write that out. That's 27 minus 15. And then you also have to minus 8 more. By the time I've done that, it's close, eh? Like 27 became a pretty large number, but this time around, with this guy being a positive number here, you're actually subtracting the 5 by 3. So that pulls it down to 12. That pulls it down to 4. Is 4 less than 0? No, it's not. It's close, but it's not. So these are not answers. I don't know that I mentioned it when I started this, but we have another name for what we'd call these points right here. These are called critical points. Critical points. And so the last thing you got to do is consider whether or not those critical points are numbers that would be true on their own. So what if I try negative 1? Well, if I try that critical point of negative 1, 3 times negative 1 squared minus 5 times negative 1 minus 8, this will give you 3. That'll make it plus 5. Then you'll minus 8. And all of this will actually give you 0, which is good because we solved it as a quadratic as though it was equal to 0, right? So when I do that, I end up getting 0. Now, is 0 actually less than 0? And the answer is, well, no. If it was or equal to, sure, that would hurt. That would count. But 0 is not less than 0. So this is where you'd have to use like an open circle. So to summarize, our final answer then would be written something like this. Anything between negative 1 all the way up to 8 over 3, non-inclusive, would work. Or you could write it as, like, say, negative 1 to 8 over 3, only don't write what I just did there. Hopefully you already see my mistake. You shouldn't have those little bars on the bottom there, right? Because it's not or equal to, right? Here are some different ways of, x, an element of the reals, however you've been taught to write these sort of things. Okay, so there's one example down. Hopefully that made sense. Hopefully that's something you've seen before. Really, today's lesson, as we kind of scroll through, we're going to remind you about the quadratic formula because you can use that. But most of the rest of this is just examples, including these last ones, which involve unique cases of absolute value. I hope you see those ones there, as well as cases of rationals, which are fractions. So, okay, so let's move forward. If we want to keep solving these things, you may need the quadratic formula. So like say this one right here, it's going to operate almost the exact same way as what we did last time, except you can't factor this one. So if I use the quadratic formula, it's negative b. So negative 4, because the 4 is negative, plus or minus the square root of negative 4 squared, minus 4 times 5 times negative 2, all over 2a, a was 5. So again, hopefully this is something that you're kind of familiar with. I am not in my videos at least going to re-go over how to redo all grade 11 and grade 12 skills. I'll give you a Cliff Notes version just to remind you. But you're definitely going to need to know how to do some of them on your own. And ask me questions, right? Please don't hesitate to ask for a refresher on something if you're like, oh my goodness, I don't remember how to do this. We'll check that. 4 times 5 is 20, times by 2 is 40, 2 negatives makes it a plus. We'll make it 56 over 10. We should be able to reduce that. 56, let's just think here. 56 is going to be 4 times 14, so you could call this 4, plus or minus 2 root 14 over 10. So you could call this 2 plus or minus root 14 over 5. There. I believe I've solved that using the quadratic formula. So like I was saying as I was kind of working at the same time here, if I lost you on that one, let me know. I'll try to help you with it, but that's definitely a previously learned skill. So let's keep going from there. Now I want to plot those numbers on a number line. So let's plot 2 minus root 14 over 5, and then let's plot 2 plus root 14 over 5. And we'll just test some values there. Okay, this would be a time where, you don't need your scientific calculator, but I have a graphing one here on the screen just to show you. It wouldn't hurt to know what these decimal number approximations are. So 2 minus root 14 over 5. It's about 1.3, give or take. And if I do the exact same thing again, oh, hang on, that's not right. 2 minus root 14, then divide by 5. Whew, almost made a big mistake there. Take it back, that's about negative 0.3. Negative 0.3. And then for the other one, it's 2 plus root 14. Whew, having a bad day typing in. Root 14 divided by 5 makes it 1.14, give or take. Okay, so let's try numbers greater than and less than these numbers. So, let's keep it simple. Negative 1 is lower than that one. So 5 negative 1 squared minus 4 negative 1 minus 2. Let's see, that'll give you 5. That'll add 4. That's 9 minus 2 will give you 7. Is 7 greater than 0? It is. So because of that, it looks like values in this section over here should hold true. So I'll put some check marks there. I just put a whole bunch of them there just to indicate that all of them should work. And while I'm at it, I'm going to indicate that this value right here, the exact value of 2 minus root 14 over 5, that one should hold because it is an or equal to symbol there. Now, you'll probably figure out pretty quick on quadratics that it either is the middle section or the outside sections. That is not always true because we're going to do rationals and absolute values in a bit. But this is a very common sort of pattern where you have a graph where I'm asking you where it's greater than 0. And if I were to ask you where it's greater than 0, it's greater than 0 in this section over here, this section over here, but not in the middle. But let's just go through the motions of practicing. If I pick a number between these two, the best number to use is probably 0, because 0 is between negative 0.3 and 1.14, so I'm expecting this not to work now. If I try 0, that's a 0, that's a 0. Is negative 2 greater than 0? It is not, so therefore I have x's there, right? And then over here, I should pick a number that is greater than 1.14, like say, let's go crazy, let's go 100. This is where mental math skills come in. If that's 100, and you square 100, that gives you 10,000 times by 5, so that's 50,000. But then you're going to minus 400. That doesn't really do that much difference. And then you're going to minus 2 more. It still doesn't make that much difference. This is a very large number, right? Is this large number still going to be greater than 0? Yeah, it is. So those are true. Okay, let's talk about how to write this then. We would write this then as from negative infinity up until 2 minus root 14 over 5. And we would get to include the 2 minus root 14 over 5. We would then union that with 2 plus root 14 over 5 and take that all the way up to positive infinity. And that would be our solution set. So basically everything on the outer extremes is the solutions for this one. So again, hopefully that's somewhat familiar. Essentially the idea is, as a quadratic is, if you're looking for where it's greater than or less than a section, here's where it's less than, here's where it's greater than. So it could either be the middle section or the outer sections. But if you flip that quadratic upside down, now if I ask you where it's greater than, now it's the middle, and if I ask you where it's less, it's on the outside. How does that change, though, if it's rational? Rational graphs, they can look crazy. The rational graphs can kind of have this sort of shape to them. Rational graphs can look like this, where they have some asymptotes going on. So let's try those ones. I used this vocabulary earlier. They're called critical points, right? For quadratics, we use critical points for the roots. So when you solve it as though it's equal to 0, that gets you started. Here you have to use the roots, but you also have to use the non-permissible values. I don't know if that's an abbreviation you've seen before. NPV stands for non-permissible value. And you're essentially looking for, well, where are the parts where you cannot let the denominator equal 0? You probably know what I'm talking about here because you've done this before. So let's just hop into an example. So let's start off right off the bat with the non-permissible values. What can x not be equal to? Hopefully you don't need me to say it out loud for you, but I'll pause for a second for you to think about it. Or, by the way, and in times like these, make sure you pause the video, right? Pause the video if you need to just before I kind of get to something. So if I go fast, then you can slow it down. But hopefully you're clear that the one thing x can't be is 1. Right? If x is equal to 1, then 1 minus 1 will give you 0 on the bottom. We can't have that. Essentially, this is an asymptote, if you're familiar with that vocabulary. So there's one of my critical points. So if I plot a number line, which I'll do in a second here, I need to check where x is equal to 1. That's one of the spots on there. But I also have to check and see where this thing's equal to 0. So now let's pretend for a bit here that this actually just equaled 2. If I did that and did some algebra, and hopefully, again, I'm not going to be able to redo every single little bit of algebra you've learned in the previous years of your math education, but hopefully you're able to kind of figure out how to solve this guy here. It looks like x is going to equal 5. I think I got it. Let's check that. 5 plus 3 would give you 8. 5 minus 1 would give you 4. 8 over 4, that would be 2. Okay. So it looks like I found 2 critical points. One of them where I have a problem. X can never be 1, which means I have an open circle right there. It definitely cannot be 1 just because this whole thing right here has a non-permissibility clause of x not being allowed to be 1. There's another key point I should check in, which is at 5. Now, if this were or equal to, I would circle in the 5 because that would work. But as I tested the 5 here, 5 plus 3 was 8, and 5 minus 1 was 4. 8 over 4 is 2, but 2 is not actually technically less than 2, so you'd have to have an open circle here as well. So, okay, now we're in the same spot that we were before. We need to test the different regions in the number line. But I got to point out, there's no guarantee that when I do this here, that it's going to end up being like this section and not that one. It could be any or all or none of the above. So we just have to test these critical points. So let's test a critical point less than 1. And I think the best point to test less than 1 is 0. So let's try it. 0 plus 3, 0 minus 1. This will be 3 over negative 1, which will give you negative 3. Is negative 3 less than 2? It is, so that should mean that all points in this region should fit. And I haven't done this yet, but I mean, you could test more than 1 point if you want. You could test negative 7. That's less than 1, right? Negative 7 plus 3 would be negative 4. Negative 7 minus 1 would be negative 8. Negative 4 over negative 8 is going to give you 1/2, but yeah, 1/2 is less than 2, so it looks like even negative 7 worked. The whole idea behind this, by the way, is that we're just going to test 1 point in the region rather than test every single point, right? That's ridiculous. We can't test every single one. So, okay, let's test another point. We need a point between 1 and 5. Doesn't really matter which one we pick. I certainly wouldn't pick 2.937, right? I'd pick a whole number, like say 3. 3 and 3 gives 6. 3 minus 1 gives 2. 6 over 2 gives 3. Is 3 less than 2? And no, it's not. So apparently we don't have answers here. All right. I can check another point just to confirm it, just make sure I didn't do it wrong. I'll get rid of some of this. It's getting a little busy here. 4. 4 plus 3 is 7. 4 minus 1 is 3. Is 7 over 3 less than 2? 7 over 3 is 2 1/3. It is not less than 2. It's slightly more than 2, actually. So yeah, it looks like this region's out. All right, now, I mean, you may be tempted to say, well, there must be this region over here, but we need to double check. I cannot promise you that's the case. So let's try something bigger than 5, like 10. 10 plus 3 is 13. 10 minus 1 is 9. Is 13 over 9 going to be less than 2? Yeah, it is. 13 over 9 is just greater than 1. So yeah, it looks like actually, although I've told you that you can't guarantee it, it looks like this one actually does follow the same pattern as the previous quadratics. So our answer is going to be from negative 7 up until 1, non-inclusive, and then pick her up again at 5 and go to positive infinity. I just realized my mistake. Maybe I'll pause for a second here, see whether you can find what my mistake is. If you didn't catch it, it was negative 7 is not the lowest I go to. It's negative infinity that's the lowest I go to. I happen to write negative 7 as an example, but this does keep going from negative infinity up till 1, picks up from 5 and goes to positive infinity. So, okay, let's try another example. Let's try this one. And again, this is going to be really, really repetitive today, hey? Like we're doing the same thing over and over again. I should point out, if you feel like, during any of these videos, if you feel like you got it, you don't have to watch all the videos. I mean, I certainly recommend it. I mean, it's kind of the point behind how we're designing this course, but I have had some students, what they do is they, if they look ahead and they go, yeah, I can do this, they watch the rest of it on fast forward. I think there's an option on YouTube where you can speed it up to like double time or something like that. And then, all those little things that I have to do to explain, and, it takes a lot longer. You can make a 10-minute example compressed down to a minute if you want. And then, so long as you feel like you get it, you can do that if you'd like. So. Okay, let's do this one here. 4x plus 3 over x minus 4x plus 3. I'm just going to factor that. Hopefully you know how to factor, because it means we actually have two values right off the bat we need to be aware of. 4 and negative 3. Oh, that's gross. Let's write that better. Negative 3 and 4. Right off the bat, those are some values that definitely are not possible because they're not permitted. You can't use negative 4 and 3. I do actually have one more value I need to look for. This is going to be another section here. We need to see where this does actually equal 0. So if I pretend this is equal to 0, some kids actually, they get really stumped as to how to solve this. They go, I don't know what to do. But, I mean, think about multiplying off your denominator. If you multiply this whole denominator up to the other side, all of this comes up here and it multiplies by 0, right? So once this gets multiplied to the other side, but then when you times it by 0, this whole thing is just gone. So really what we're looking for is when 4x plus 3 equals 0, which means we're looking for negative 3 over 4, right? And in terms of this one right here, because it was just less than, then I can't fill the dot in. I want to go back here. Did I do that properly? Yeah. For this one here, since it was just less than, I don't fill the dot in. But if there was the bar underneath, then we'd fill it in. So now I have 4 regions I need to look over. I'm just going to erase to make some room here because this is going to be a little more challenging. Once you get the hang of this, by the way, this goes much faster. Like I'm taking my sweet time walking you through this, but it goes faster after a while. Now let's pick some test points. Let's pick negative 4. 4 times negative 4 would give you minus 16 plus 3. So that'll give you a negative 13. And on the bottom, negative 4 squared will be 16. That'll be a negative 4, but you're really adding, right? Negative 4, so that bumps you up to a running total of 20. Then you minus 12, it gives you 8 on the bottom. Is negative 13 over 8, is that less than 0? And it is. So we should have answers anything below 3. Then I need to pick a number between negative 3 and negative 3/4. I'll go with negative 2, I guess. You can go with negative 1. I don't really care what number you pick. You just need to test one. So if I use negative 2, that's negative 8 plus 3. That gives you negative 5 on the top. Really what we need to do is figure out whether the bottom is going to be positive or negative. Because if the bottom is negative, then 2 negatives will make it positive. But if the bottom is positive, then a negative and a positive makes it positive. If you kind of get where I'm going here. So negative 2 squared, that gives you 4. Negative 2, add some more. So you're up to a running total of 6. But then when you minus 12, it makes it minus 6. So here's what I was going for. Now that we have a negative over a negative, negative divided by negative makes it positive. And so is positive 5 over 6 less than 0? It is not. So these answers are out. Next section. I'm going to use colors to help keep them separate here. We need a number between negative 3/4 and 4, and I'm going to pick the number 0. Just because 0 is so nice. Really what you're left with is 3 over negative 12. 3 over negative 12 is a negative number. Negative numbers are less than 0, so it looks like these ones should work. Number bigger than 4, let's go 5. 4 times 5 is 20, plus 3 is 23. 5 squared would be 25. You'd be minusing 5 to get you 20, and you'd be minusing 12 to give you 8. 23 over 8 is a positive number. Positive numbers would not be less than 0, so we don't have answers here. So our final solution is you can go from negative infinity up until you reach negative 3. Don't get to include negative 3. You get to re-pick it up again at negative 3 over 4 and go all the way up to 4, and then you're done. All right. Like I said, sometimes on these videos I'm going to start speeding things up, right? I'm not going to show every step. So rewatch if you need to. Have your list of questions to ask me, right? Either via email or when we have time to talk on Tuesdays and Thursdays or whenever we talk. And yeah, rewatch. Let me know if I can help. But let's move on to our next topic. Once in a while I'll skip an example, by the way. If I feel like in the course of doing the video I feel like I have the idea, what I can do is I can just leave an example blank and say, well, why don't you try this one? So if you'd like to, maybe pause the video, try this one, and if you think you got the hang of it, then move on. If you want the practice, try it. I mean, you can email me and say, hey, did I do it right? One really nice thing to try to do, once you do some work on a sheet of paper, take your cell phone, snap a photo of it, and then email me the photo. Hopefully you guys all know my email address by now. It's shulkc@lrsd.ab.ca. I find this works well for students. I mean, do your work, snap a photo of it, send me the photo to my email, and just basically say, hey, did I do it right? It doesn't take me very long just to peruse it and say, yeah, no, you're good. So anyways, I'm going to skip this example here and let you try that one on your own. Let's move to a new topic called absolute values. And these are another types of functions, and they're technically piecewise functions. It's basically another if-if statement. If the number that you're talking about is a positive number that you're absolute valuing, then you leave it positive. But if it was a negative number, then you add an extra negative to make it positive. That's essentially how these things work. So like if I ask you to absolute value 9, you would say, well, it's just 9. But if I ask you to absolute value negative 9, it's actually also 9. And the reason is because what you're really doing is you're making it negative. Negative 9. That's what this means here is if it was negative, throw another negative on. This negative here will make this negative here turn it into a positive. So hopefully you remember absolute value because this is grade 11. So let's do a couple examples here. Let's say that I want you to determine the absolute value of negative 6. The answer is just good old 6. Right? Basically, absolute value means you can have no negatives. Right? But that's a little different when you're working with variables here. If I ask you what x values would have made it 5, there's actually two answers. X itself could have been 5, or it could have been negative 5. And here's why. If it was 5, if you absolute value 5, it would give you 5, sure, right? But if it had been negative 5, when negative 5 gets absolute valued, I guess, however you say that, then negative 5 would become positive 5. So you can actually have two answers here. So these answers here don't necessarily have to be positive only. X can be positive or negative. I mean, in a graph, it can go all the way from negative, whatever low number you want to any large number. That's not the issue here. The issue is that this number here and this number here, those should be positive then. So here's what that means then for an example like this. We actually do two cases. We do the positive case where we say, well, if it was positive, we just pull off the absolute value signs. We just say, well, then x was 5, right? Because wouldn't 5 minus 2 give you 3? Okay. But there's also the possibility that what if x minus 2 was equal to negative 3? What if this thing was supposed to be negative? What if it was supposed to be negative, but then our absolute value made it back to be positive? Well, then in this case here, x could also have been negative 1. Right? Check this out. If x was negative 1, negative 1 minus 2 would have made this negative 3. But when you absolute value negative 3, then it makes it positive 3. So I have two answers. Well, we can use this then when I get to inequalities. So I'm going to hop down and do the inequality now. What ends up happening in a situation like this is we're going to get multiple answers and we're going to plot them on a number line again. So first we have to find out where our critical points are. And one of them will be, let's just pretend that it's equal and pull off the absolute value signs. That'll be equal to 2 divided by 2 divided by 2. It looks like one of my values, one of my critical points, is when x is 1. But there's another critical point. What if 2x plus 5 was supposed to equal negative 7, but it didn't equal negative 7 because we just made it positive? Well, then 2x would equal minus 12. So I've got a couple of critical points here, one at 1 and one at negative 6. Now when I plot my number line, negative 6 and 1, I have very similar things to what we've had before. We need to check different regions. So let's try, like, say, negative 10. 2 times negative 10 is negative 20. When I add 5, negative 20 plus 5 would give me negative 15. But then when I absolute value that, it would give me positive 15. Is positive 15 less than 7? No. Pick a value between negative 6 and 1. 0 works good. 2 times 0, well, that would be 0. Then you'd have 5, right? Well, 5 would remain absolute valued, I guess, right? So it would remain positive. So 5 is 5 less than 7? Yep. And then for the last one, we need to pick a number greater than 1. So 7 million. 2 times 7 million is a lot. Add 5 more, it's a lot more plus 5. Well, that was a positive number. That was a lot. So now it's just a really large positive number, and that number is definitely not less than 7. Because of the lack of the bar underneath it, we do not get to count the 6 and the 1. There's your answer. Okay, let's do one last example here, and we'll kind of combine this all together. So I should have a couple left here. Yeah, here we go. Let's try this one here. So I'll skip over the other examples here. Try them on your own time if you need. If you feel like you got the hang of this, let's go to the big one that involves everything. It's an inequality, it's an absolute value, and there's a rational. So we got a number line we got to find. First thing we should do is look for all of our critical points. One of our critical points right off the bat is where x equals 4. And hopefully that's clear to you, because if I try plugging in 4 right here on the bottom of the fraction, I can't, because that's it's not valid to divide by 0, right? So there's 1. So then I should do something like solve as though it's equal. So let's pretend this is equal to 3. If I times that up there, I'll get x plus 3 equals 3x minus 12. 15 equals 2x. So x is 7.5. There, I found another critical point here, x at 7.5. If I test that, 7.5 plus 3 would give me 10.5. 7.5 minus 4 would give me, 3.5. And 10.5 divided by 3.5, I believe, is 3. So that one works. There is a third critical point I need to look for, and it's dealing with the absolute value sign. What if the absolute value sign had taken this value here that was supposed to be 3, and what if it was negative 3 originally, but we made it into a positive 3? Well, then when I bring this up here, you're going to get negative 3x plus 12. So we'll make that 4x over there. Bring the 3 the other way, make that 9. 9 over 4. What's 9 over 4? 2 1/4? There. That one should also be a critical point. Let us test it real quick. 2 1/4 and 3 will give you 5 1/4. 2 1/4 minus 4 will give you negative, let's see, what is that, negative 1.75. If you take 5.25 and divide by negative 1.75, it should give you a negative 3. But with the absolute value signs, it would make it positive 3. So here are our critical points. Now that we've identified those, just like always, let's figure out what regions of the graph we have. And I mean, so far, it's always just been like alternating, but I guess I can't promise that that's always the case. That's just random happenstance based on the examples I've given you. We need to actually test them all out and see which sections there are. So let's do it. Right off the bat, we need a number less than 2 1/4. I'm thinking 0. It gives you 3 over minus 4. But it'll become positive 3 over 4. So the question is 3 over 4 less than 3? Or sorry, greater than 3? And it is not. We need a number between 2 1/4 and 4. I'm thinking the best number there is 3. 3 plus 3 is 6. 3 minus 4 is negative 1. It's supposed to be 6 over negative 1, which would be negative 6. But when you absolute value, you get 6. Is 6 greater than 3? Yep. Pick a number between 4 and 7.5. 5. Why not? 5 and 3 is 8. 5 minus 4 is 1 is 8 is 8 over 1. Is that greater than 3? Yeah, it is. I don't trust it. Let's do another one. Right? Maybe you don't trust it, right? Let's try 7. 7 plus 3 is 10. 7 minus 4 is 3. 10 over 3 is 3.3 repeating, but that is greater than 3. This is the first time we've had one of these. Look, there's 2 sections in a row that are the same as each other. However, you can't have the number 4, right? Because if you try the number 4, try as you might, 4 minus 4 is 0 on the bottom. You can't use 0 on the bottom. So it gives you kind of a weird section here. You can't have all the low-end numbers. You get a whole bunch in the middle, but there's actually a gap right there at 4. All right, lastly, let's try a number greater than 7.5. And, I mean, sometimes I just pick a crazy number just to prove a point. Let's go with 100. 100 plus 3 would be 103. 100 minus 4 would be 96. 103 over 96 is slightly more than 1, right? It's slightly more than 1, maybe like 1.1 something, right? But is that going to be bigger than 3? No. So here is our answer. There's a couple ways you can do it. You could say you're going from 2 1/4 up until 4, and then start again with 4 and go up to 7.5. That'll work. Yeah, you could go from 2 1/4 up to 7.5, and then afterwards say there's an exception, x can't be 4. You could write it as 2 1/4 to 7.5 with the exception of 4. Like, there's a lot of different ways you can write it. I think my preferred way is going to be this one here. Interval notation is very powerful. It's a nice shorthand way of being able to do things. So, okay, there's more or less our lesson for the day. Pardon my cough. Yeah, we're done. So let's just re-talk about some of the main things we talked about during this lesson. The first one is being able to solve inequalities. You're basically looking for this number line concept, right? Where you're looking for sections. We're testing a point to see whether it's either below or above the axis. The 3 main things you'll be doing is quadratics, but you can also do rationals, which have the unique thing about the bottom of the fraction. It gives you non-permissible values. You got to consider those. We can also throw on the absolute values as well, which means you have multiple cases where you have to make this equal to 3 and negative 3 due to the possibility that the negative was turned back into a positive. And like I have in these last ones here, you could end up actually having it being both. Okay. So I did skip this example and I did skip this example, but as I look at my time, we're at 43 minutes, which is about what I want to do. I want to try to keep all the videos to under an hour. A typical class at a university would probably be about 50 minutes. At the U of L, they run classes for 50. So I'm going to try to keep it to something like that. So this is as university similar as I can get. So sometimes they have classes for just over an hour, but this is about the right amount of time. So I guess the point I want to make then is if you want to try this 3x plus 1 greater than 8 example, give it a try now, right? Do some practice on your own. And since this is the last lesson in the unit, if you haven't already been working on the assignment, you definitely should now. So you have until the Friday at 3 p.m. to pass in the assignment. If you have questions, please email, ask me questions. You do not have to do this by yourself. If I can give you one piece of advice, it would be to figure out where to go to for help, because you will need help. I promise you, you will. You will not get through university without a study partner, going to tutorials, going to your professor and asking him for clarification. Like, that is an important skill to learn. And I find a lot of students, they expect that, like, they feel like they're supposed to just be able to do it on their own, and that's not how this works. So right now, I am your resource. So make sure you ask me for questions, okay? Email me. Let's talk on Tuesdays and Thursdays over our video conferencing stuff. And yeah, hopefully this is a good first week. The next set, we'll be working on limits. And this is really where calculus begins, is when we start doing limits. So, okay, we'll talk to you all later.